So let's talk about a little bit about when integration by substitution works. Pretty much, integration by substitution is a tool that can help us find an antiderivative when the derivative we're looking at came from the chain rule. So think about the chain rule. That's us taking the derivative of some function, but there was composition involved, which means there was some sort of inside of our function, and then we had to multiply by the derivative of the inside. Which means that almost every time you use integration by substitution, your integrand, the derivative you're looking at, should be some kind of multiplication problem. That was me putting a multiplication dot in there. Now, sometimes the thing you're multiplying by is a constant, and it's not easy to find. But take a look at this problem. My integrand is a multiplication problem. It's a product. The two things getting multiplied together are sine of x and e to the cosine of x. So the big hint that integration by substitution is going to be useful for you is if you can think of some function so that the derivative of that function is one of the factors in your product. So when I look at e to the cosine of x, I think about e to the something. Well, what's the derivative of e to the something? Well, it's e to the something else. I don't have an e to the something as my product, as a factor in this product. But if I think about u, setting u equal to cosine of x, and then I think about the derivative of cosine of x. Well, the derivative of cosine of x is negative sine of x. That's not an exact match, but look at this other factor in my integrand. It's definitely very closely related to the derivative of cosine x. So that's my sign that this might be a good substitution to make. So I'm going to try it and see if it works. Most of the time, if you make this substitution and then try to rewrite your integral so that it uses only one variable, it's either going to work or not work, and you'll kind of know right away if this is a good approach to take. So let's just try making u equal to cosine x. In this case, I know that du is going to equal negative sine of x. Clearly didn't leave myself enough space to write that, because what I want to write is du equals the derivative of cosine x is negative sine of x dx. Can I isolate dx? So at this point, there's two ways to go. I'm going to show you a way that's going to always work. I'll show you a little shortcut later in case you like it. So I'm going to imagine dividing both sides by negative sine of x. And I'm going to get negative du over sine of x equals dx. I'm going to rewrite my integral using colors. You don't have to actually use colors, but I'm just going to write it these first couple times where you're getting used to it. So the integral of sine x e to the cosine x times dx. Look what I'm going to use in place of dx. Look what I'm going to use in place of u. I'm going to write my new integral. This is going to be the integral sine of x e to the u times negative du over sine of x. So I replaced my dx with this. I replaced my cosine x with, sorry, I probably should have circled that guy instead. I replaced my u with cosine x. Look at my new integral. It's like Frankenstein. It's got all kinds of junk in here. Plus I have two variables. I have u's and x's. I definitely may not try to find an antiderivative yet. But watch what happens. I need a neutral color here. See this sine of x? Is going to cancel with this sine of x. And look at my new integral. It's the integral of e to the u times negative, I'm going to bring the negative out to the front, du. Anything that had an x left in it canceled out, and now I have an integral in terms of just the variable u. This is a negative, is a constant multiplier. The antiderivative of e to the u with respect to u is just e to the u plus a constant. That's a pretty good answer, but notice that my original problem had x's in it, so I'm supposed to report my final answer in terms of x, so this is going to be negative e to the cosine x plus a constant. And you can check. Imagine taking the derivative with respect to x of negative e to the cosine x. That would be negative e to the cosine of x times, what's the derivative of cosine x? Because I'm using the chain rule. Hold on, I have to hide me. Derivative of cosine x is negative sine of x. Notice the negative and the negative would cancel, and I'd get sine x e to the cosine x, which is an exact match for the integrand I started with. This is how you check your answer to any antiderivative problem you do. If you're taking the AP test and you do an antiderivative problem, especially if it's a multiple choice problem, you check it every time. You could even even if you didn't know how to find antiderivatives, you could get antiderivative problems correct on the AP test by simply taking the derivative of all the answer choices. Just clarify one more final thing. What was our final answer here? It was the function whose derivative is sine x e to the cosine x. So final answer there in green in the box. All right. Sometimes the derivative that we're looking for that's supposed to be a product, like one of the factors in the product of our integrand, isn't an exact match. But if it's only off by a constant, like in the last example, we were off by a negative. Sometimes we're going to be off by a number, a constant multiplier. That's okay. We can still use U substitution. So here, this is a good example to note that sometimes, if you're not sure what your U is, good things to try are things that could be grouped together in parentheses, or things that might already be grouped together in parentheses. So if I think about what's inside the parentheses here, I might decide to let U equal 7x minus 2, in which case du is 7 dx. Watch what happens. Notice here that derivative, my du, contains only a constant. Sometimes it's going to contain some sort of variable expression. Here where it contains only a constant, this is probably going to go faster and it's going to be even easier to check your answer. So I might take that constant multiplier that's already there and bring it out. And notice instead of 7x minus 2 cubed times dx. Oh, look, here. I didn't remember to isolate my dx, so I'm going to divide both sides by 7 and get du over 7 equals dx. All right, so here we go. I'm going to have 28 times the integral of, instead of 7x minus 2, I'm going to write u, so it's u cubed. And instead of dx, in this case, I'm going to write du over 7. So the 28 and the 7 can cross cancel. That's going to give me 28 divided by 7 is 4 times the integral of u cubed du. Well, how do you take the antiderivative of something getting cubed? That's going to be u to the 4th over 4. Here's this 4 that was already a multiplier. Comes down. I need plus a constant. I need to report my answer in terms of x. So I'm going to simplify this 4 and 4 and go back to, instead of using u, using 7x minus 2. So it's going to be 7x minus 2 raised to the 4th plus a constant. I'm going to double check my answers. So remember, if I wanted to take the derivative of 7x minus 2 raised to the 4th, that's going to be 4 times 7x minus 2 cubed times the derivative of the inside, which is 7, which makes 28. 7x minus 2 cubed. Final answer.